Greetings, physicists. This lecture video is about how to solve or analyze graphs where the object is moving with a constant velocity. This is a very big skill to have in the world of physics. So we're going to start with a few problems, and I'm just going to walk you through the solutions. So, number one, we're looking at a car, or a graph of a car's motion. And this is just a qualitative. Well, you could do a quantitative as well, but it says describe in words the motion of the car represented in this graph. So we're going to be looking for features of this graph that stand out. Now right away, I'm going to look at that right there, the starting point. This car did not start at 0, wherever 0 happens to be. We're not given a lot of information about this car. 0 could be home, if your car left from home and drove to the store or somewhere else. You know, that could be it. If it was a race car, 0 could be the starting line. So wherever this car was, he was 10 away. And if we look at the numbers on our axis, he was 10 kilometers away from wherever 0 is, whatever the reference point is, whatever we're comparing him to. And this is a displacement graph. This has position here and time here. So when we're looking at that point, that 10 is a position. It's not a velocity or something. So that's right away something you could say. Well, to begin with, the car starts 10 kilometers away from the reference point. And it's 10 kilometers in the positive direction, wherever that is. So if the positive direction was east, then he's 10 kilometers east of home, or 10 kilometers in front of the starting line at the racetrack. All right, so if we keep going, there's some intervals here. So I'm going to mark off some intervals in red. We have this interval, and this interval. So kind of 3 separate lines that showed the same trend during that interval. So if we look at the first interval where I've marked, which is this one here, the line is straight, or it would be straight if I had better manual dexterity to draw it with. Well, let's assume it's a straight line, and it's going downward, so it's a decreasing slope or a negative slope. And from what we can tell then, it starts at 10 kilometers and ends at negative 20 kilometers during that period. So this car is going in the negative direction. The car, if it started 10 kilometers in front of the race, it's going backwards in the race, which is probably, so this probably isn't a race car. But if it's starting 10 kilometers east of home, it's traveling west. That's what we can say there. And it's doing so at a constant rate because this line is not changing its slope. So its speed is constant during that time. And it does so for, looks like about 30 minutes. Okay? Now, at 30 minutes, which is right here, there's a change, and the change is to the slope of the graph. That slope of the graph goes to 0, and it stays 0 until here. Let's think about what that means on a position graph. At 30 minutes, the car was at a position that is 20 kilometers in the negative direction from the reference point. So if we could say it's 20 kilometers west of home, if we wanted to be consistent here. But look at 40 minutes. From 30 to 40 minutes, it stays at a position that is 20 kilometers west of home. So it's staying in the same position. This is a car that's not moving. When your slope is 0, you have 0 velocity. So for the second interval, the second time interval on this graph, that car is turned off. So they went where they were going and they stopped. Maybe they got out to go get food or something, who knows. But that's what happened as described by the graph at this interval right here. That's a 0 movement because this is a position graph. And then for the last interval here, we're going to notice a couple of things. That would be this interval stretching from 40 minutes all the way up to 80 minutes. Okay, the first one is that this line is got a positive slope. So this car is traveling in the positive direction. It's going from negative 20 kilometers, or 20 kilometers east of or west of the reference point, however we were setting up our coordinate system. And it travels all the way to a position here, which is 0. And that could be anything. That could be home, that could be the start-finish line, whatever. So, but that car is going in a positive direction. If it kept going, it would increase its position even more in the positive direction. So we could say there, for that last interval, the car has a positive velocity. It's moving in the positive direction, and it does so for 40 minutes until it reaches a final position of 0, which is the reference point here. Now we could even compare here, if we wanted to do some more describing. If we look at that first interval compared to that last interval, the first interval travels from a positive 10 position to a negative 20, which is a total displacement of 30 kilometers, or total distance of 30 kilometers. And it does so in 30 minutes. So 30 kilometers in 30 minutes for this first movement. It does it in the negative direction, so if you were going to talk velocity versus speed, its speed is 1 kilometer per minute, its velocity is negative 1 kilometers per minute. Over here, though, we're going for 40 minutes, that's a 40-minute interval, and we're going a distance of 20 kilometers. So we go 20 kilometers in a total of 40 minutes. So that's half a kilometer every minute. So this interval is half as fast as this interval. The car was going twice as quickly in the beginning as it was at the end. So these are all things that we can notice from this graph. All right. I'm going to go ahead and switch to the next problem here. So we're graphing another car. In this case, we've got 2 questions. One, we're actually going to try to get some numbers. Find the car's velocity versus time graph, and then describe the car's motion in words. So we're going to be generating another graph here based on this one. And we notice, if we're looking, this is a position and time graph. So it's another graph just like the one we just saw. That's not what they're asking us to make. They're asking us to make one that says velocity and time. So we're going to have to do some thinking here. So let me go ahead and make a graph. Well, let's analyze this one first. So like the previous graph, there are 3 intervals. So we can mark them off here. We've got the first interval is up to 2 seconds. Second interval is from 2 to 4 seconds. Last interval is from 4 to 6 seconds. And that probably will not change when we go to our velocity versus time graph. We're still going to have a velocity over a 6-second interval. What I see at the beginning, I see a constant negative velocity. When I get to the second interval, I see a 0 velocity. And when I get to the third interval, I see a constant positive velocity. And that's just because I can tell positive from negative because the slope in the first interval is going downward and the slope in the last interval is going upward. All right, so let's, and you could even figure numbers for these. If we were to look at the first interval, its vertical change here is from 0 to negative 4. So that's 4 meters. And then it travels that in 2 seconds. So it's going 2 meters per second speed or negative 2 meters per second velocity. So I can make a little note here. This first interval is a minus 2 meters per second. It stopped for the second interval, so that's a 0 meters per second. For the last interval, it starts at negative 4 and goes all the way to positive 6. Big jump there, right? That's a jump of 10. So it changes its position by 10 meters over 2 seconds. So 10 meters per 2 seconds, well, that would be a 5 meters per second for this last interval. And that should be enough for me to draw my new graph. So let's go down here, and I'll see if I can leave that on the page. I am going to be going from 0 to 6 on the x-axis. That hasn't changed. It's the same time. And then on my velocity should be my vertical axis. Look at this. I have a small velocity of minus 2, a large velocity of +5. And so those should be my boundaries. So let's do that here. Okay, so 1, 2, 3, 4, 5, 6. Is that spaced right? Okay, looks right. And then, do I have room? I'll just do it by ones. This will be -1, -2, and then I'm going to go, that will be 0, and then 1, 2, 3, 4, 5. I'll go ahead and just mark it like this because I don't have a lot in between. All right. And then 1, 2, 3, 4, 5, 6. And because it's a graph, I'm going to label it properly. So this should be velocity in meters per second, and this is time in seconds. All right, so when I do my new graph, my first interval again starts with a 2 meters per second, and that's not changing. I know that's not changing because the slope is constant. It's a straight line. So that velocity should be exactly the same whether I'm at 0 seconds or at 1 second or at 2 seconds. So let's draw that. At 0 seconds, I should be at -2. Let me draw a little dot there. At 1 second, I also have a velocity of -2. At 2 seconds, I also have a velocity of -2. So this is a flat line on my velocity graph. I have a constant velocity there. At 2 seconds, my velocity changes instantaneously. There's a corner there, which doesn't happen in real life, but we'll pretend that it's valid. So we'll say that there is an instantaneous change to a velocity of 0. So I'm going to put a little dot at 0. And it stays at 0 velocity up to 4 seconds. So at 4 seconds, I'm still at 0. So if I draw this, it's going to have to go right on top of the x-axis here. So that's my next part. And if you want to connect them, use a dotted dashed line. Little dashed line there. Going up, hard to see because the 2's in the way. And then at 4 seconds, again, another corner. And I change immediately to 5 positive meters per second. So that's right up here. And it stays there for 2 seconds. So like right there. So I have that. And again, if you want to connect them because it's an instantaneous change, just put a little dotted dashed line like this. That's fine. So that's my velocity versus time graph for this car. Starts at -2 meters per second. It's going backwards, or left of the origin if you wish, or east, or whatever you define your coordinate axis as. It gets to 2 seconds, it stops moving, and then it gets to 4 seconds, and it's now going in the positive direction at 5 meters per second. And of course in real time, or in real life, it would take time to accelerate, but we'll get to that later. All right, so that was find the car's velocity versus time graph, describe the car's motion in words, which we sort of did, but if you're describing it in words, during the first 2-second interval of its motion, it is going backwards, or it's going in the negative direction with a velocity of -2 meters per second, or you could say it's going backward with a speed of 2 meters per second, that's fine. And then at 2 seconds, it stops moving, and it stays motionless for 2 seconds, and then for 2 more seconds, starting at 4 seconds, it is now moving in the positive direction at 5 meters per second. And all of those intervals, each of those 2-second intervals is a constant motion. It does not accelerate during those intervals. Okay? So, now we go forward. Let's do number 3. All right, comparisons. So they've given us 4 graphs here, and we want to know which object moved the farthest, or ended up the farthest away from where it started during this 2-second interval. And these have been drawn in red, and you can see that we've used that dotted line to connect things, and sometimes it's on the x-axis. So let's do this in blue. Now you can solve this a couple of ways. The easiest way, I think, is to recognize that these are all velocity graphs. These are all velocity on the x-axis and velocity on the y-axis and time on the x-axis. And when you have a velocity versus time graph, you can measure displacement as the area under the curve. So I'm going to shade in those areas for each of these graphs. Okay. That makes this actually very quick to solve, because we're just looking for the square or the rectangle or the parallelogram with the largest area. And I've got a 1 by 2, I've got a 2 by 2, I've got a 2 by 1, and I've got a 1.5 by 1.5. So clearly this one visually is the largest, but if you do the math, that's 4, an area of 4, and all the rest are less than that. So this thing went 4 meters. And then I think the first one went 2. 1 times 2 is 2. The second one went 2 as well. And the last one, 1.5 by 1.5, is 2.25, I believe. But graph B is the clear winner in this case. And use that. This will save you a lot of time on tests if you can remember that the area under a velocity versus time graph, or the area between the line and the x-axis, represents how far the object went during that time interval. Okay, a couple more here. Hockey. Love me some hockey. Okay, so we've got this hockey player. That line is apparently his position versus time. And the problem doesn't state which direction is positive. I'm going to assume that positive is toward the opponent's goal and that negative is back towards his own goal. That makes the most sense to me. So we're looking here, and there's some questions. The first one is sketch an appropriate velocity versus time graph from this position versus time graph. On a test, if you see that word sketch, you want trends, but not necessarily numbers. And appropriately, they have not put numbers on the question. Like the graph itself that they generate for you does not have numbers. So this is all relative. This is all qualitative. Okay, if I can, there we go. Scrolling is the thing. All right, so we're going to make a velocity versus time graph, and I'm just going to lay it right on top of itself, underneath here. What I see here for velocity, let me mark this up. At the beginning, his velocity, right, is going downward. It has a downward slope. So he is going farther to the negative direction, maybe towards his own goal, until he gets to point A. And at point A, the slope, the instantaneous slope, is about 0. And then it's going back up. So he has a positive velocity after point A until he gets to point B. Point B is the steepest, it looks like, he ever gets to. If I were to draw like a line like this, it doesn't get much more vertical slope-wise than point B, because after point B, this curve starts to go back the other direction until it gets to point C and it's flat. Interesting things to note. So if this is velocity and this is time, down here, let's draw that. At the beginning, the velocity is negative. So I'm going to make this my velocity here. It's going to start somewhere below 0. It's going in the negative direction. At point A, which I'm going to draw right below where point A actually is up here, at point A, we'll call that point A. Point A, the velocity is 0. He reaches 0 velocity. So I'm going to put that on the x-axis there. And then his velocity keeps going up until we get to point B. Point B is over here somewhere, and it's as high as it can possibly go. So I'm going to draw this at the very top of my velocity graph. And then after point B, it does not get higher. It actually, the velocity, the slope, remember the slope of a position graph is velocity. That slope starts to get smaller until it gets to point C. And at point C, his velocity is 0. This is point C right here. So I have to draw point C back on the x-axis. So if I'm connecting these, this looks like I have an increasing velocity all the way up to point B. Let's draw point B right there. And then I have a decreasing velocity down to point C. And here's point A, and here's point B, and here's point C. And from the region from 0 to A, 0 time to A, you have all of those are negative velocities. So he's going backwards during that first region. And then he gets to A, and then from A he's going forwards again and until he gets to B. He has a positive increasing velocity from A to B. At B he's going as fast as he possibly can, and then from B to C he's still going forward, but he's slowing down. Because all of these velocities are in the positive region from here up until here. They're all above the x-axis. And you can see that from here, from A to C, the slope is positive all the way from A to C. At A it's 0, at C it's 0, but at every point in between there, that slope is positive. So he has positive velocity during those points. Very important to be able to tell that, because that can be confusing when you're looking at two different types of graphs. All right, so that was A, sketch an appropriate velocity versus time graph. At B, at which point or points is the player moving the fastest? It's got to be at point B. And we can see that on our velocity graph. Point B is the highest he ever gets. Is the top of his velocity. And if we look at the position graph, point B is the steepest the slope ever gets. And we marked that earlier. So that's important. And then part C, is the player ever at rest? He is definitely at rest. He is at rest at two sort of points. Now, I need to kind of adjust my velocity graph here. If you notice here at point C, that line flattens out at C and then keeps going. So technically his velocity is 0 for a while because his position is not changing during that point. So it's hard to mark it because it's all in blue on the velocity graph. So what we can say is at this point his velocity is 0. But it's only 0 for that instant. Okay, it's not 0 at any other time before or after that leading up to point A. So we would call that an instantaneous velocity of 0, but there's no interval there. It's an isolated time point. It literally exists only for one moment. But once you get to C here, the velocity from C until the end of the graph is 0. So he does stay at rest once he gets to C. Maybe he does one of those quick slides and stops himself, you know, cool hockey style. But anyway, that's how we would answer that. The player is at rest instantaneously at point A and from point C forward. Good deal. All right. Whoops, I don't want to do that. I want to do this. There we go. And last one, number 5. All right, we're looking at another car going forward, and this is a velocity versus time graph. So this is a car whose velocity is increasing, and it says we're calculating how far it goes, but only for the first 3 seconds of the graph. So I'm going to go ahead and do something here. Remember, this is easier to calculate with a graph. If you have a graph, you can do this very easily by measuring the area underneath a velocity graph. Area underneath a velocity graph is displacement. And they want the first 3 seconds, so from 0 to 3 seconds. So I'm going to go ahead and mark that off and shade it. That area there. Great. A little harder than the ones we had before just because it's a triangle, but not really that hard. So if we're doing the area of a triangle, it's half base times height, which in this case is half of the time, which is 3 seconds, and the height of this triangle is 12 meters per second. So 3 seconds times 12 meters per second. And so half of 12 is 6 times 3 is 18. Seconds cancel. Always use your units to help you. That would be 18 meters that this car travels during the first 3 seconds of its motion. If you're sitting in a typical room, one-story room, most rooms have a ceiling height of about 3 meters. So this car travels the equivalent of about 6 stories. That's not too bad. Again, not a very challenging problem if you recognize that reading a velocity versus time graph, you can get displacement as the area underneath that line. Okay, hopefully this is helpful for you in dealing with any kind of velocity or position graph. We said at the beginning that this would be for constant velocities, although we did get into some examples where there was changing velocity.